Now we're going to look at the tangent theorems. So the first of the tangent theorems, theorem, assumption, but it's the one that has the idea of the radius always being perpendicular to a tangent. Now, this is not so much a proof, more as a logical way of explaining it. So I've just drawn a radius in OX. Now we want to say OX is going to be perpendicular to the tangent, so which I'll end up calling XY. Now, if I draw a chord in that's perpendicular to that radius, then I know that the perpendicular from the centre will bisect the chord. So it'll be nice and symmetric either side of the radius. And I'm saying that distance is X. But if I make that distance closer and closer to the radius, then the length of the chord, which at the moment I'm calling 2y, so y above, y below, that'll get closer and closer to being 0. Now if I slide that chord along then, so I want to get x closer to being the radius, we can see the chord's getting smaller. And I'll move it again. And I could get to a point where technically the chord now is just that single point x, but it's still perpendicular. Now, had I not drawn a chord in, had I drawn a secant in, then at this point I would now have a tangent, and the chord would just be the single point. So say, it's not so much a proof, it's more a logical way of thinking about it. If I push that chord out to the circumference, it's still going to remain perpendicular, and then at some point it'll become a tangent once it hits the circumference. So that idea becomes OX is perpendicular to XY because a radius will always be perpendicular to tangent at the point of contact. Alright. From any external point, just like we saw with the parabola, you'll remember, from any external point we can draw in two tangents. All conics are the same, so the circle is another type of conic. So from this external point T, we can draw in 2 points, and what we're saying is that distance AT will always be the same as BT. Alright, let's prove that one. So I'm going to join up a couple of radii and also join that external point to the centre. Creating 2 triangles, I'm going to use congruent triangles again. So we know, well, what we just proved. So angle OAT would be 90 degrees, but so would OBT, radius perpendicular to tangent. OT is common to both triangles, and the 2 radii that we drew in, well, they're going to be equal as well. So I have right angle hypotenuse side. Therefore, the third sides, AT and BT, must also be equal. They become the matching sides in congruent triangles. Now, the other thing I've put there is that line OT that I've drawn in will always be an axis of symmetry to the shape. If you've got 2 circles touching externally, remember we said circles that touch externally have a common tangent at the point of contact. Well, it turns out that the 2 centres and that point of contact will always be collinear. So we know that to be a fact. Now the reason, again, I don't think I actually proved it in the notes, but it's a quick one. We know the radius is perpendicular to the tangent to the left-hand circle, but I also know the radius is perpendicular to the tangent to the right-hand circle, so therefore I've got 90 plus 90, which is 180, so that must be a straight line. Okay, that'll do us for today. So we'll play with some problems that involve tangents.